Hello students, let me commenting open some details in realization theory, impulse response matrices, Hankel matrices, and a singular value decomposition of such a Hankel matrix, which has the same column space as the observability matrix. So, assume given impulse response matrices I use H as the impulse for an impulse response matrix with index I equal to d a in I minus 1 times b for some integer numbers I equal to 0, 1. I start with 1. And 2 dot up to a number L plus J, two integer numbers. Then we can define two matrix equations. Or Hankel matrices. First of them is H1 given L, which can be proved to be equal to the product of the extended observability matrix O and the extended controllability matrix C. OL times CJ. And there is a second Hankel matrix related to A also. That is H2 given L equal to OL A CJ. Like this. Where those two Hankel matrices are defined from the impulse response matrices. And let me define those two Hankel matrices with an example. Defining H1L and H0Ln. Given L plus J, say 8 impulse response matrices. And let us also specify L equal to 2. Then we start to fill out this one. H2 given L is then equal to. We start with the Hankel matrix H2. And L is also equal to 2, means that we should have 2 block rows. Like this. And use all the impulse response matrices. H4, H5, H6, H7, H8. And it is a Hankel matrix because of this structure. A rectangular matrix like this in this example. And then we define the first Hankel matrix. It should have the same number of columns as this one. H1, H2, H2, H3, 3. 5, 6, 1, 2, 3, 4, 5, 6, and 7. This also means that here the number of block columns is 2. Then we can also find J as the number of block rows, which is 2, 4, 6. And J is equal to 6 in this example. Furthermore, the observability matrix in this example is simply D over DA and C2, Cj, since J is equal to 6. Is then B, AB, A square B, A third B, 1, 2, 3, 4, A 4 B, 5 and 6. It looks like this in this example. Let us now go for the identification of the system order N, which is the rank of OL and also the rank of CJ, if we assume that the system is both state observable and state controllable. And let us find D and B and A. And the key here is this so-called singular value decomposition, which is the tool to deal with the rank of matrices and to calculate the famous spaces of a matrix. We take the SVD of equation 1 here. 1 and 2. One in order to estimate or calculate system order N, OL, CJ, and then D and B matrices. Now, this Hankel matrix H1 given L may be factored into the matrix U, the left singular vector matrix, a diagonal singular value matrix S times V transpose, where V is the right singular vector matrix. And as I have said, partition those matrices as follows. Here, the number of columns in U1 is N. And this S1 is a diagonal matrix with N singular values. And zeros above the diagonal and below. And it is your choice as the user to specify the number of non-zero singular values. The zero or smaller neglecting singular values is collected into S2. And then we have U1, S1, V1 transpose plus U2, S2, V2 transpose. Since S2 contains smaller singular values, we neglect this one. And we simply have that this Hankel matrix is equal or approximated equal to this decomposition. Now we can compare with this one. Comparing here, we obtain at least 3 important realizations. One, the output normal realization, which I prefer. They will give the same quality of the resulting model. The difference is a scaling factor. Yeah, for instance, if we can choose the observability matrix to be equal to U1, and then we have to choose this controllability matrix equal to S1 V1 transpose in order for this one to be similar to this one. We have a second choice, which is called input normal. That is the choice where we simply choosing the controllability matrix equal to V1 transpose. Then the observability matrix would be U1 S1. This gives the so-called input normal realization. We have a third realization listed or known in the literature called balanced realization. This one means that the singular values are balanced into both the observability matrix and the controllability matrix. Thinking about this S1, which for if there are 3 singular values, say, then the matrix looks like follow 0, 0, S3. Then we can put this one equal to S1 upon the n½ times S1 upon the n½ the square root, where S1 1/2 is the square root, simply a matrix like this. This one could be simply generalized. Means that the extended observability matrix then is put equal to U1 times the square root of S1. I will write it like this. Or S1 upon in 1/2 like this. And then the extended controllability matrix would be equal to square root of S1 V1 transpose then. This is the balanced realization. But remember, the quality of the resulting model would be the same. And for simplicity, when calculating the A matrix, I prefer the output normal realization. But it's your choice. The difference is only a scaling of the state vector. Let us go for the A matrix then. And the reason is that at this stage, the system order is n is calculated, and both the observability and controllability matrices, as we have seen here. And then we find the D directly from O, and B directly as the first block of Cj. Because of the definition of the observability and controllability matrices. I can, before proceeding in order to calculate A, I can remark. Remember the observability matrix is a matrix like this. D, D, A, dot, 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 down to D in A, L minus 1. When this one is known from this step, you can simply read out D here. And similarly, from the definition of the controllability matrix, which is B, besides AB and A square B, dot, 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 up to A in J minus 1B, we simply find B as this first block here. Now, let us go for the A matrix. I have taken away matrix equation 2 to solve the second matrix or Hankel matrix, which is equal to OL A Cj. Solve this one for A. Here O and C are known from up here. Then we have from this output normal realization choice. We have U1 times A then, and Cj is S1 V1 transpose. Now, simply multiply from left with U1 transpose and from right with V1. We find U1 transpose times this Hankel matrix is then simply equal to A S1. Because these singular vectors or the singular vector matrices are orthogonal. The vectors are orthogonal to each other. So U1 transpose U1 is equal to the identity matrix. So U1 transpose is simply equal to the inverse of U1. Loosely spoken. Remember that U1 may be a rectangular matrix. But this is true. And we also have that V1 transpose V1 is equal to the identity matrix. Also with dimension n, in order to be precise. Yeah. From here, we find an estimate of A. Like this, and V1 and S1 inverse. Simply as we have done a number of times so far. Okay. This theory was published the first time in the middle of the 1960s with a home-built algorithm. Ho and Kalman published an algorithm. It was they don't use the singular value decomposition, but later on, efficient software for this singular value decomposition was published at the end of the 60s or early 70s. Then it was natural to do it like this. Okay, thank you. There is a password here. Thank you.